All right, so today's topic is digital signatures, and we are going to talk about what kind of digital signatures are used in blockchains or cryptocurrencies. So our aim is to first talk about digital signature algorithm, then elliptic curve digital signature algorithm. Both of these algorithms, in these algorithms, the security depends on the discrete logarithm problem. So it is now to talk about the discrete logarithm problem. So recall that in public key cryptography, we rely the security on the hardness of a problem, right? So in this case, the security will depend on the hardness of the discrete logarithm problem. But the good thing is that now we can talk about discrete logarithm problem because we have enough algebra. So we learned groups, generators, rings, fields last week. So now we can properly describe the discrete logarithm problem. So let G be a group and small g its generator. Given A, it should be feasible to compute G to the A. So, here I'm using the multiplicative notation. So in your group, assume that the group operation is multiplication. So when there is a generator, it should be easy to, multiply G with itself A many times, okay? But the thing is that if I give you the results and also give you the G, but don't tell you what A is, it should be computationally it should not be computationally feasible to find A. So discrete logarithm problem is this, okay? So actually, if you take the logarithm here of both sides, logarithm of B to the base G gives you the A. This is why we call it the logarithm problem, okay? We will call it discrete because we will not work on, real numbers or any continuous group. We will be working on, discrete groups. So, but here the important thing is that the hardness of this problem, or more technical term is intractability of this problem, of the discrete logarithm problem, depends on the group. So if you choose a bad group or, some kind of group operation, this operation can be very easy to be performed. So let's look at actual non-discrete examples to see that how the group actually affects the hardness of this problem. So let's consider rational numbers as the group operation addition, okay? So when I give you B and G, your aim is to find A such that A times G equals to B. Since now I'm using the addition group operation, this is why we have A times G. I'm adding G to itself A many times, okay? In the multiplicative notation, this turns into G to the A. That is the difference. So as you can see that this is just a rational number. So you know B and you know G. You are trying to find A. What you can do is as follows. Divide B with G, right? A simple division operation will give you the A. That's it, because we are working with rational numbers, right? So a simple division operation will give you the answer to this question. Let's make it a little bit harder. Now let's focus on the multiplicative operation as the group operation, and real numbers is the group elements. So now you are given B and G. Your aim is to find A such that G to the A equals to B. Okay. So now that is what I mentioned in the previous slide. What you can do is as follows: calculate the logarithm of B to the base G, and this will give you A. Okay. So a simple logarithm operation, which you can do in a very, very fast way, regardless of how big the numbers are in any computer. So as you can see, logarithm problem in for this board of groups and board of operations are very easy to solve. So questions, can I make it harder? So let's go on to finite groups. So in this case, it becomes more meaningful for our examples. So now I'm looking at the group ZP with addition. Now your aim is to find again A such that A times G equivalent to B modulo P. Now as you can see, I cannot do logarithm or anything, but what I can do is as follows. Now instead of the division like here, what I can do is I can calculate the inverse of G. So you might think that is it easier to find an inverse of an element? Actually, we have the extended Euclidean algorithm, which works really fast, regardless of the size of P. Okay, so you can easily calculate an inverse of an element. But if if P is small, you can multiply G with any element and find the inverse. But still, extended Euclidean algorithm gives you this inverse. What you can do now is to multiply both sides of this equation with the inverse of G. Once you multiply G with its inverse, it is the identity element, so you end up with A here. Okay, so idea is to multiply B with G inverse, but B is actually A times G, right? So you end up with G inverse times A times G. G's cancel each other because due to inverse, so you end up with A modulo P. So as you can see, this problem is also not that hard because, I mean, I haven't shown you how fast the extended Euclidean algorithm works, but it is really fast. So you can always solve this problem, regardless of how many hundred digits of P is, okay? And yeah, here it says the G inverse can be easily computed by using the extended Euclidean algorithm, which is, by the way, very nice algorithm. If you're interested, just, could be a good exercise to implement, yeah.
If it's really equal to A, are they commutative?
Yes. Yes, that is the good thing. Here in the last week, I told you that, when it is commutative, we call it an abelian group, right? So these groups are abelian anyway. So it doesn't matter if you multiply G with G inverse or G inverse with G. So it is like, multiplying 3 with 1 over 3 or 1 over 3 times 3. It is always the same. So all of these groups I have covered so far are all abelian or commutative. So this is not a problem here. Since it is a simple multiplication operation, it doesn't matter if you're multiplying from the right or left. But in abstract algebra, this is a good question because not every group is commutative. So you have to talk about right multiplication or left multiplication in that kind of situations. But luckily for us, this is not an issue for this course. So let's make things interesting. So let me give a better example where I say that, okay, let's again use ZP, but choose the group operation as multiplication. So the question is the same. You are given G and B. Of course, you know the P. Your aim is to find A so that G to the A is equal to B modulo P. Now, as you can see, the problem has become harder because I don't have any nice trick to do here, right? Because, multiplying with an inverse, or I cannot take logarithms or anything, because this mod P actually kind of, hides your steps. So this is why we call it interactability. So best known algorithms are sub-exponential with respect to P. So this is actually why we talk about, hardness of algorithms. So there is no polynomial time algorithm so far known that breaks this question. So this is what makes it a hard question, but not, one of the hardest questions because you can solve it with sub-exponential time algorithms. So let me give you an example. I choose an X value. I take the X power of 3 modulo this number, which I claim that it is prime, but it's prime. So I'm saying that this is the result. Now find X. So you can do the following, try one by one, take the first power, second power of 3 and check if it is equals to this one modulo this one. But this kind of brute force attack is an exponential time algorithm, right? So the question is, can you do better? Actually, there are sub-exponential time algorithms that is better than this kind of brute force attacks. Okay. So in this example, the answer was this. As you can see, if you were trying by hand, for instance, you have to try this many power operations and so on. So it is not that easy as you can see. Yeah. It is never, it is not, calculating the logarithm in this case makes no sense because we are moved on to from a continuous world to a discrete world. Now, since everything is modulo this, actually this number is actually, 3 to the power x times, sorry, some multiple of this prime plus this. So there's a plus operation here. So taking the logarithm there actually would not benefit you anyway. So this is just the remainder of a division operation. So for instance, it could be something simple like 2. What would you do then? Right? Taking the logarithm of 3 wouldn't give you anything. I mean, if you are interested in this, just do some calculations and see that it wouldn't help you at the end. Okay, it is not a simple question. And we can talk about it in the break if you want. Okay, so I'm moving on to this elliptic curve discrete logarithm problem. So recall that I defined a group with the points using the elliptic curve, right? Now I define the discrete logarithm problem, which starts with a simple sentence saying that let G be a group and G its generator. Now, as you can imagine, I will take this group as the elliptic curve, and I will take a generator point on that elliptic curve and define the discrete logarithm problem there. So this is where things got interesting, because I already said that, okay, I'm going back, said that the hardness of the discrete logarithm problem depends on the group. So now I said that this problem is hard, but there's a sub-exponential time algorithm to solve it. So we use this one in the digital signature algorithms, but we will use elliptic curve discrete logarithm problem in elliptic curve digital signature algorithms, because this problem will be harder, and instead of ZP, I use points of the elliptic curve. So let's move on to this example. This definition. So given an elliptic curve E defined over a finite field FQ, a point P on the set of the points of this elliptic curve over the field FQ of order n, and the point Q equals to D times V, where you are trying to determine D. So this is the discrete logarithm problem for the elliptic curve. So let me actually go over it again. So this means that there are n points on this elliptic curve, okay? And P is just one of them. So there's an integer D. So you add the point P to itself D many times and obtain the point again on the elliptic curve, which is Q. So you know Q, okay? You know P. Question is, what is D? I'm asking you how many times I add the point P to itself so that I obtain this point Q. So this is the elliptic curve discrete logarithm problem. Again, what the brute force is simple. You start adding P to itself, and at the D trial, you will realize that it will give you the point Q. But of course, this is again exponential time algorithm. All right. So why this is better than the other group? Because here we have the polar draw algorithm that can solve any discrete logarithm problem about this many operations. Okay, so if you are working over the field FQ, you can do around Q over 2 operations. So if you use big O notation, it will be square root of Q over 2. Okay, actually 2 will also cancel, so it will be square root of Q. So this is important because of the square root. When I talk about 128-bit security, I told you that you can use AES 128. But due to this square root, if I want to use elliptic curves, I have to double the key size to make it 256 due to this algorithm. Okay. Index calculus algorithm can solve the discrete logarithm on the ZP, not on elliptic curves, with sub-exponential time complexity. So this is why this problem is easier here, but harder on elliptic curves, because I don't have a sub-exponential time algorithm to solve it for the elliptic curves. Okay. Index calculus algorithm uses relations between small primes, which is not applicable to elliptic curve discrete logarithm problem. This is why the problem is harder here. Thus, using elliptic curves allows us to work on groups with smaller number of elements. This makes your key sizes to be smaller, and this actually shortens everything. So let me give you a few examples which actually generally not used on blockchains, but I'm trying to show you where this discrete logarithm problem can be useful. So Diffie-Hellman key exchange is one of the basic examples where the security relies on the discrete logarithm problem. So assume the situation A wants to talk to B in a secure way over the internet, but they haven't agreed on a secret key yet. So you can think about this Amazon.com. You want to visit there and buy something, but you haven't agreed on a secure key to communicate for encryption. So, but you are connected via internet, but it is insecure communication channel. Question is, can you agree on a secret key through this insecure channel? But at the end, you will have a secret key so that you can communicate in a secure way. So discrete logarithm problem can be used here for the Diffie-Hellman key exchange, and idea works like this. So I think that this Alice and Bob, they want to communicate. So Alice picks a random number A and sends G to the A to B. B picks a random number B and sends G to the B to A. Now A computes G to the B, which he received from Bob, but Alice chose A randomly by herself, so she can calculate the 8th power of this value that he received from Bob. So she ends up with G to the AB. Bob thinks the similar thing because Bob received G to the A from Alice, and B is randomly selected by him. So he can calculate the bit power of G to the A, and he ends up with G to the AB. As you can see, both sides agreed on the same thing. Now they can say that, okay, this can be like, 3,000 bits value. They can say that let's use the first 128 bit to, for encryption. So let me show it in a better way, but this time using the ZP group with multiplication operation. Idea is as follows. You have public parameters G and P. Alice randomly chooses a value A, calculates G to the A mod P. Let's denote it with capital A, and sends this to Bob. Bob does the similar thing, but this time with a random value he generated, sends B through this communication channel, and both agree on the same secret key. So as you can see, the security relies on the hardness of the discrete logarithm problem, because anybody listening to this communication, since these are public parameters, they know G, they know P, and for instance here they capture A, which is G to the A mod P. So they know capital A, small g, P. Now if they can capture small a from here, actually they can also calculate this value, right? So all of the security relies on the hardness of this discrete logarithm problem. So most of the internet security actually comes from this simple operation. Okay, so two communicating parties who hasn't agreed on a secret key through a secure channel now can agree on a secret key by themselves. Again, this is not used in blockchains. I just want to show you how the discrete logarithm problem can be useful. So let me also give another example where you can use discrete logarithm problem for encryption. Again, this is beyond the scope of this course, but if you're interested, or maybe you might want to, write something on the blockchain in an encrypted way, this is what you can do. So first, since this time it will be an encryption algorithm, first you have to generate your keys. So you randomly choose a value X. This will be your secret key. You compute G to the X and end up with another group element, and you say that this is my public key. So as simple as that. So you randomly choose a value. This is your secret key. This is your public key. So when you want to send a message, for instance, your message will be M. In order to send the message M, what you do is as follows. You randomly choose a value R. Calculate V, which is M times Y to the R. Y is your public key. Then also calculate U, which is G to the R. Okay. This is the person who is sending you the message. So they don't know your secret key, right? They want to send you a message. So they are using your public key and all of the other parameters to send you their message. In the decryption side, what you do is as follows. You take this U and calculate the minus X power of it. So since X is your secret key, you know this value. But if you write U as GR, this means that actually G to the power minus XR, right? So also Y to the R is here, which is GXR. So minus XR cancels each other, and you end up with M. So a very simple number theory. Okay, just this axis this minus sign when you add with X actually cancels each other. That is the point here. So this way you can actually use your private key and public key to write a message. If you want to, if you're interested, you can write such a message on the blockchain in an encrypted way. So only the person who has the private key can read it. That is the idea here. So let me finish this part with these observations. So as I said, NIST always suggests 128-bit security for personal use. And if you're going to use military security, you need 256-bit secret keys. So let's stick to this security level, 128-bit. So this means that in the symmetric key encryption, you can use advanced encryption standard with the secret key size of 128. But if you are going to use discrete logarithm problem, as you can see, your group size has to be 3072 bits. So the actual problem lies here. So if you want to build a hardware for this kind of operations, think about for military. So you need this much security. So you need to build a hardware that works on numbers that are 15,000 bits. So it is very hard to, costly to implement on the hardware. So for this reason, instead of using discrete logarithm problem, you can use elliptic curves, right? For, either elliptic curve Diffie-Hellman key exchange or El-Gamal encryption, or as we are going to see, elliptic curve digital signatures. You can simply choose your secret keys as to be 256 bits. This is why, Bitcoin elliptic curve I showed you actually of this size, okay? So, for instance, if you want the RSA encryption, again, your factoring modulus, the group size should be like this, 3072 bits. So this is the whole idea. This is why Bitcoin uses elliptic curves, okay? Or Ethereum or any other cryptocurrency who actually uses the libraries from Bitcoin implementation. This is the whole reason, because here you have a sub-exponential time algorithm to solve this problem. Here you don't have any sub-exponential time algorithm, but you have Pollard's row algorithm, which actually has the square root on top of it. This is why, due to that square root, this number is multiplied by 2. Okay, as you can see, if you want this much security, we multiply it by 2 again, due to Pollard's row algorithm, and that's it.